Before we get into the code for linked lists, it's helpful to understand what an abstract data type is. Abstract data types are a theoretical computer science concept. They simply describe what kind of data a data structure can hold and what operations are allowed on that data. If you were creating an entirely new abstract data type from scratch, you could decide what kind of data you wanted it to hold and what operations would be allowed on it. But since we're working with linked lists, which are already defined and understood in the computer science community, we'll stick to the basic operations that already exist for the linked list abstract data types. An abstract data type actually has nothing to do with code. It simply expresses ideas about and requirements of a collection of data and how we're allowed to interact with that collection. Since abstract data types have nothing to do with code, they're inherently language agnostic. The implementation of an abstract data type is called a data structure. Throughout the rest of this course, we'll be focused on creating data structures for linked lists using Python. There are a couple advantages to thinking about data with abstract data types. The first is abstraction. Abstract data types always have certain predictable properties and allowed operations that we specify at the outset. How the abstract data type is implemented to create a data structure doesn't matter, as long as the data structure allows us to interact with the underlying abstract data type in the ways we expect. In other words, we don't have to understand the code that creates a data structure in order to make use of that data structure, as long as the data structure allows us to interface with its data in a way that is consistent with what its abstract data type spells out. Another advantage of abstract data types is consistency. Because we don't need to understand a data structure's implementation in order to use it, the implementation of the data structure could change, and as long as the new implementation supports the existing interface, we don't need to change our own code. Let's wrap up with a couple notes about data structures. Remember, data structures are simply implementations of an abstract data type. For every allowed operation in the definition of an abstract data type, we'll have one method within the class we use to create the data structure. It's important to note that there's often more than one way to implement an abstract data type. You'll be seeing my approach in this course, and there are certainly other ways to implement linked lists. In order to better understand what a linked list is and how it's different from Python's built-in list data type, let's dig a little deeper into what we usually mean when we talk about lists in Python. When people talk about lists in Python, they're usually referring to the built-in list data type that we're all quite familiar with. The syntax for the built-in list data type consists of paired square brackets with comma-separated values in between them. The items inside a Python list can be of different data types. Here, you see integers, strings, a float, and a Boolean value, even another list. The definition of a list is a mutable, ordered collection of items that do not need to be of the same type. What we mean by ordered is that the list preserves the order in which items were added to it, not necessarily that the items in it are in numerical order or alphabetical order. As you might know, the Python language is written in C. Behind the scenes, the Python list we're familiar with is implemented in C using what's called a dynamic array. Discussing dynamic arrays in depth is beyond the scope of this course, but it's enough to know that dynamic arrays take up a contiguous chunk of memory. Each item in a dynamic array is stored in its own slot of that contiguous chunk of memory. Remember, with lists and dynamic arrays, we always start counting at 0. This means that an item inside a dynamic array is stored in a slot that is directly after the slot of the item that precedes it, and directly before the slot of the item that follows it. Dynamic arrays allow us to index directly to a specific item by using an integer value that represents the position of the item's slot within the dynamic array. This is possible because the dynamic array knows how many slots in memory it has. This is the indexing syntax that you are probably very familiar with. We can also add items to the end of a dynamic array in constant time, because dynamic arrays reserve more contiguous memory than is actually needed, meaning that there's usually more slots available beyond the last occupied slot. These characteristics of dynamic arrays are available to us via Python lists, and again, you're very likely familiar with them. Like Python's built-in list type, linked lists are also a mutable, ordered collection of items, but the similarity ends there. In the next video, I'll show you how linked lists differ from Python's built-in lists and also explain the main features of the linked list's abstract data type. Let's talk about nodes and how they're used to construct linked lists. I spoke earlier about how abstract data types tell us about the data they store and the operations we can perform on that data. Linked lists don't store their data in a contiguous chunk of memory like Python's built-in lists do. Instead, linked lists store their data in a series of nodes. Each node contains the data being stored, as well as what's called a pointer. The pointer indicates the location in memory that holds the next node. Because linked lists don't store their nodes contiguously in memory like Python's built-in lists do, these pointers describe the order in which the nodes should be accessed. This creates a structure that resembles the inherently ordered nature of a Python built-in list. When you see diagrams of linked lists, they often appear to show node pointers pointing to the next node itself. While this is a helpful way to visualize a linked list, remember that pointers are actually pointing to a slot in memory, not the data that's held within that slot. We've discussed the use of a next pointer. But what if we find ourselves somewhere in the middle of a linked list and want to go backwards to a previous node? We can do this by attaching a second pointer, called a previous pointer, to the node. If we only need to be able to move forward through the linked list and not backward, we can create what's called a singly linked list. Singly linked lists make use of the next pointer only. Thus, singly linked because the nodes only have a single pointer connecting them. If we want to be able to move in either direction, forward and backward, we can create a doubly linked list. Doubly linked lists make use of both the next and the previous pointer for each node. As you can imagine, we call them doubly linked because the nodes have two pointers connecting them instead of one. We'll cover each of these types of linked lists in greater detail later in the course. The entry point to a linked list is called the head. The head is not a separate node, just a reference to the first node of the linked list. The end of the linked list is indicated by a node whose pointer points to none instead of to another node's location in memory. If the head reference points to none, then we assume the linked list is empty because there's nothing there. An analogy we can use to better understand how nodes work is a garbage truck driver's route. When a garbage truck driver first starts their route, they're given an address to drive to for their first stop. The act of handing the garbage truck driver this first address is like what the head of a linked list does. It leads them to the first node of the linked list. The garbage bins at that first address that are awaiting pickup is like the data aspect of the node. Those garbage bins are the reason the driver is going to the house, just like assessing or using the data in the node is the reason to visit the node. The next address that's on the garbage truck driver's list is like a node's pointer. It's telling them where to go to find the next set of garbage bins, or the node that has the next bit of data that we want. Finally, when the garbage truck driver is finished with their route, there are no more garbage cans to collect. We can think of this as the final pointer in a linked list pointing to none to signify the end of the list. Of course, in the real world, we know that the garbage truck driver has to go back to where it came from originally, but for the sake of example, let's ignore that part. Though it may appear obvious, it's worth mentioning that a linked list is a linear data structure. Even though its various nodes may be scattered around in memory, we can conceptualize the linked list as a line of data, if you will, because of the pointers that connect each node's location in memory and specify the order in which the nodes need to be accessed. Now that I've explained that nodes are the building blocks of linked lists, the next step is to discuss the operations we'll need to be able to make on the linked list itself. Now that we understand how nodes can be joined in order to create a linked list, Let's talk through the basic functionality we need a linked list to have. At a minimum, we need to be able to add a node to and remove a node from the linked list. Regardless of whether we're working with a singly linked or a doubly linked list, we need to be able to add a node to the beginning or to the end of the linked list. We may also want to add a node just before or just after an existing node whose data item matches something we're looking for. This is called a key. Similarly, we'll need to be able to remove a node from the beginning or the end, and we'll probably want the ability to remove a node that appears just before or just after a node that contains a key. Aside from the basic functionality of adding and removing nodes from linked lists, we may also want to know whether or not a linked list is empty, how many nodes are in it, or we may want to be able to find the index of a node that has a particular key. We'll create a method for each of those capabilities later on. The linked list is what's called a sequential access data structure. This is because we can only access a node by first accessing all the nodes that came before it. So when does it make sense to use a linked list? If you need to be able to insert items in between other items, if you're working with a collection whose size is unknown, if you don't need random access, because again, linked lists have sequential access, and if you're not concerned about memory usage. Linked lists have a unique property about them, and that is that they are also recursive data structures. A linked list is either empty or it's a node that contains a data item and a pointer to a linked list. In this example, you can see how the node on the far left is actually pointing to an entire other linked list. Likewise, the node in the middle is itself pointing to a node that then points to another linked list. We won't discuss recursion in this course, but knowing that a linked list is a recursive data structure may come in handy in an interview. I encourage you to study more about the recursive properties of linked lists if this interests you.